So before we get into any of the content, I just want to say that I plan on doing a series going over each topic in the OCR A-level computer science spec. A link to that spec will be in the description of the video. Now, I don't know how far I will get. Hopefully I manage to finish at least all of the paper 1 content, but that might take a while, so no promises. I think it's important that you guys know this because all of the computer science videos from now on will be catered towards this exam board. Anyways, the first chapter of the spec talks about CPU registers and buses, so that's what this video is going to cover. But before we jump straight into registers, I think it's important we discuss what the CPU actually does. The CPU, also known as the Central Processing Unit, is one of the most important pieces of hardware for any computer device. It's often described as the brain of the computer, because just like how a human brain has billions of neurons, the CPU also has billions of transistors. Now here we get to our first roadblock, because most programmers don't know about the small intricacies of how a CPU works from an electrical circuit standpoint. That's because if we really wanted to fully understand how a CPU works, we would need to talk about how transistors and circuits work together with voltage. But programmers aren't really concerned about any of that. They're only focused on the concept of how their program interacts with the CPU. And this simplified concept of the CPU is called the programming model. This also tells us that when we are learning about CPUs, what we are really learning about is a generalization of the CPU. In reality, most CPUs differ slightly to one another because they are made with different purposes in mind. A CPU designed for a supercomputer will obviously differ from one designed for a washing machine. The general idea of how a CPU works is that we feed it binary instructions. And binary instructions are basically instructions that are just a list of ones and zeros. We feed the CPU binary instructions because computers only understand simple instructions, on or off, true or false. The idea is that a computer just executes simple instructions really fast, which gives the illusion of a computer being able to do complex things. This brings us to the ALU, or the Arithmetic Logic Unit, which is a component of the CPU responsible for carrying out arithmetic and logic operations. Examples of arithmetic operations include addition, subtraction, multiplication, and division. Note that division for CPUs is much more processor intensive than other arithmetic operations, and all that means is that programmers should be more aware of how much their program performs division. Although modern processors have gotten so fast that it really doesn't matter most of the time. When we talk about logical operations, this is closely related to the topic on Boolean algebra, which is in 1.4.3 of the spec, which we will cover on a later date. The ALU also performs comparison operations, like greater than, less than, or equal to, and lastly, bitwise operations, which we will go over in further detail in 1.4.1 data types. The control unit is sort of like the conductor of an orchestra. It links all the parts of the CPU together and allows them to communicate with one another. To summarize, we often say that the control unit is responsible for the flow of data within the CPU. It ensures instructions are executed at the right time, and it also sends control signals to various components of the CPU, like the ALU for example. In other words, it might send a message to the ALU telling it to perform an addition operation. The general idea is that it works with registers and buses in order to manage the movement of data within the CPU. Finally, we come to registers. Registers are also components of the CPU that just provide temporary storage for it. They're often designed for a single specific purpose, and because they are located inside the CPU, accessing data stored in registers is much more faster than accessing data from external storage, like your hard drive or your RAM. Some examples of registers include the accumulator, which stores the result of the ALU, the program counter, which holds the address of the next instruction that is going to be executed, the memory address register, which holds the address of the location where the CPU wants to read data from or write to, the memory data register, which holds the data that is taken to or from the address specified by the MAR. And finally, the current instruction register, which holds the instructions that the CPU is currently executing. The idea of these registers might not be clear at the moment, but when we later put it into context with the fetch, decode, execute cycle, it should make the purpose of these registers much more accessible. Before the video ends, I want to cover some exam questions relating to registers. After all, the series will be dedicated to the OCR exam board, so it's important we get some practice in. I recommend you try giving these questions a go. They're all relatively short questions, just 1 or 2 marks. Anyway, the first question just asks what a register is, and surprisingly a response of registers are temporary storage located within the CPU scores 4 marks. Here's the mark scheme, and you could have also mentioned how they're single purpose and fast to access. The second question asks us to state what the program counter holds, and the program counter just stores the address of the next instruction to be executed. The mark scheme for this one is pretty lenient, but I'd recommend answering with as much detail as possible because the mark scheme's OCR releases are pretty inconsistent with how much information they want. Our last question here asks us to state the register which stores the result of the ALU. This one is pretty straightforward. The mark scheme only accepts the accumulator, but they also accept an abbreviated version.